Welcome everybody to today's low-latitude ionosphere research working group seminar. Today's speaker is Professor Jann-Yeng Liu. We call him Tiger. Yeah, we will see whether he's real tiger or not. Actually, he's a real tiger. And he's my colleague, my dear colleague at National Central University. We know each other for a long time. And at National Central University, he did his bachelor degree I think in geoscience, right? It's a geophysics.
At the Mercer Physics.
Right, Mercer Physics. And then he went to Utah University, Utah State or Utah University? Utah State to get his master's degree and doctoral degree on atmospheric physics and atmospheric physics. And he returned to Taiwan almost immediately, and since then have been staying in Taiwan for so Taiwan is his base, academic base, and he did extremely well, as you will hear from him. And he is, in fact, he's expert on many things, many different things on physics and space rather. And one of the special contributions from him is about, is the topic of today's talk, about the possible detection of precursor signature of earthquakes. And I think I think I can say that he's the founder of this field, to some extent, since he has suffered a lot from criticism. So I mean he's deserved this. Okay, Tiger, I'm not going to say anything more about bad things about you. Go ahead with your talk.
Okay.
Yeah.
Okay. Hi everyone. This is Tiger speaking, and yeah, just this as Ip mentioned, this is a very challenged and also very arguable. The topics. So I'm going to talk about detections of the possible precursor signature of earthquake and in low latitude ionosphere. Since today's working groups in low latitude ionosphere, so I choose some event specifically over this latitude. The talk actually was contributed by the Shen Hui and Zhang Fuyuan and Sun Yang-Yi and Chen Jiehong and Dimitar Uzunov and also Katsumi Hattori and Sergei Putinets. We've been all together, been so-called. You can consider this as a kind of very daring people together. Today's my talk is going to introduce a little bit low latitude ionosphere. That those is very the so-called morphology and this large structure of signature. One is a so-called plasma depression bay, and the other one certainly is being very well known, so-called wave number 4 of a non-migrating type. So that's a short, in short, that's a WM4, and this is going to be our so-called the major the target. That's that's August 5th, 5th August in 2018, magnitude 7.0, and it's following earthquakes 6.6 in Lombok, Indonesia. And together we are so lucky because we also have very intense magnetic storm, about 174 nanotesla. This is a severe intense storm. The reason why we have this one is actually provide us as a good chances to look at the so-called ionosphere storm So if we can somehow be able to understand observe the magnetic storm, then we will have to really have chances to look at whatever we observe during the earthquake period, especially the precursor period. The main instrument we are going to use is the China Seismo electromagnetic satellite that will be able to measure several parameters. For in-situ measurement, we are going to be able to see the electron density, ion density, and electron velocity and ion velocity. And we are going to use it almost all the the so-called quantity, plasma quantity or plasma parameters observed by this satellite. Meanwhile, we will use it so-called very general public been routinely use it. That's a global ionosphere map, of electron density, total electron content. So following that, we are going to see the ionosphere weather. Then we see all the detail about plasma depression bay and wave number 4. If we can properly detect, those low latitude ionosphere the feature, then that's meaning we possibly be able to detect, the so-called precursor, issue or the trigger by the earthquakes. So following that, we not only use one spot, one point. We actually are going to use, observe the globally. If we divide it, the every 2.5 degree in latitude and every 5 degree in longitude, then in total we are going to have 5183 letters to study the global map, and we will see how this is anomaly signature appear on the global maps. If the location of the and the target is completely different, that's meaning they are irrelevant. If they go together, tightly same location and in a very small area, then that we can say, wow, this is very, very possible. Okay, and finally we could go down to the SIP and the stone related electric field. As you can tell, everything still have a possible, even they are exactly same location. But if we can tell what's the physics, then this is the other story. Okay, so I hope I will be able to convince you what kind of physical mechanism in related to the seismo ionosphere precursor and the stone. And I think everybody will understand the stone. Then especially those ionosphere scientists finally come to a conclusion. I think that everybody is familiar with this what the WM4 non-migrating tide. That's due to the lower part of the atmosphere deep convection come from the so-called intertropical the convection zone, so ITCZ, intertropical convection zone. And this is a convection and on the the lower atmosphere, and we have a 4 location. And this is a strong convection somehow will disturb electric field over the around the E layer, the conducting layer, where they're going to generate the electric field, then launch the so-called dynamo modulation, then come up affect the on top of the the EIA, and that's means same 4 peak. And this been observed by the Tom Emo in GIL paper, which is 1356 angstroms as air growth, and also other the satellite. So non-migrating time, everyone understand that. And if we study the earthquake precursor signature, certainly we would like to challenge if we know this feature can be observed or not. Can we get by or not? And the other one is the so-called new finding, relatively new, the kind of phenomena, so-called plasma depression bay. This is generally appeared during the nighttime period over the since we are going to use it, the data for both for the nighttime and the daytime. So the nighttime period, there's going to have a very prominent, so-called depression, in electron density, and even ion density. You will see that actually that was almost for the first time reported by the CSAT. And I will show you, the depression bay over here. We have a 3 bay, and the moment we saw that, we said, wow, this might come from the radio occultation, some kind of a bug. So we come up and check concurrent observation of the time groovy with air growth with 1356. Then we see that also 1-to-1 correspondence. Then we consider this is not just by chance. So we look at the most prominent altitude, and we found it is about 275 kilometer altitude, especially nighttime. Just mentioned that, and this is for around near the June. That's mean May sometime. So we cut it. This is a vertical, and the latitudinal cut. That's on your right. So if there's the neutral wind below that one, and we can have this kind of so-called plasma flow. So because due to the seasonal anomaly on the summer side, we have tend to be a lower density, and this density due to will be somehow dragged by the neutral wind, then flow over to the magnetic field line, and follow that the field line, then result in a lot of sort of tremendous density lost. And so this is a kind of a new phenomenon that affects the low latitude ionosphere. So we come up. This is a major actor. That's this storm that's occurred during the August 5th, 2018, magnitude 7.0. It's over the Lombok, Indonesia. Actually, this is almost the conjugate point to the Taiwan. Because I would tend to set up the ionosphere over here, but I was advised by the Indonesia government, that's was in 1990, better not to go, because the only way to go there by then is by canoe. And there's this so-called resistance that's beyond the Indonesian government's the hands. So I finally gave up. So that's the reason why I know that one, so-called conjugate point of Taiwan. Okay, then I will draw your attention. This is the earthquake occurrences over the 7.0, and this is the intense magnetic storm occur over the 26th, and this especially after 26. This 3 days we're going to have a look, examine that one, and following the the August 5th, and 12 days later and 14 days later, we have a magnitude. The 6.5, 6.3, 6.9, the earthquake, occur. And I actually identify some so-called anomaly, was over here, and we will have to come back and for that one. CSAT, this is a satellite we are using. This is actually the first, the satellite by Chinese. They go specifically for the so-called earthquake precursor and space weather. And actually, the reason why they're doing this one, that's easy. You can tell that from the seismo electromagnetic, like somehow like a emitter. The altitude of this satellite is 507 kilometer altitude, and they are ascending and descending node time is around the 2 a.m. and 2 p.m. Okay. So this satellite was launched over there. So what I'm particularly interested in, this is electron density and their ion density. Okay. I just let you know quick look, and this is one of 5 days data, because the revisit time for this satellite is every 5 days, and this is earthquake, and this is the during the the 2 a.m.'s observation. This one example. So every 5 days you can full cover, and also for ion density. This is for the 2 p.m. During the afternoon, and you can see how that one. I will draw your attention. Look at here, 1, 2, 3, 4. That's already you can see the very prominent wave number 4. So actually, if you look at carefully, this is the kind of base signatures, and we will come back a little more detail. CSAT actually was one of so-called the first satellite that, and all the instrument was not carefully calibrated. So we using our the Formosa 3 data to calibrate that one. Unfortunately, by 2018, our Formosa 3 is with very limited data, and we are not going to be able to compare that. So, but we anyway we pick up the very similar the sunspot number, solar activity. Look at the same months. This is August 2018, 08 August. That's the target, the months. And so you can see that very clearly on the the right side is around the 2 a.m. Very clear bay over there, and the earthquakes over here. Okay, this is one of the purpose I will show you where is the earthquake. Okay, and also this is for the Formosa 3 cosmic, the 500 kilometer, which is radio occultation. The profile we get these 3 bay, so you can see how close that. And in fact, was a typo that said 2018, but this is actually 2008. And for the daytime, the 2 p.m. is the data. This is again the full peak, and the bottom one actually you can see almost identical. Okay, it's the 2008. That's mean even 10 years difference. So this is wave number 4, WM4, and this is mentioned. We confirm the CSAT can observe the space weather properly. I will draw your attention. This is nighttime. The plasma diffusion-based signature. So I can see the top panel is this, density. Lower panel is this, the electron temperature. With refraction density, you have a higher temperature. So this is very makes sense. This is called cooling. Cooling actually is a sustained being used for the electron density, but not very often by the ion. So let's check the ion density versus ion temperature. Actually, they are good. Okay, that's meaning our study and the data, at least for the relative one, is very okay. And the CSAT, the daytime. So we once again look at the full peak. This is very prominent for the electron as against cooling, and this is for the the temperature, electron temperature. So both daytime, nighttime, the signature for the bay and for the the wave number 4, WM4, they are okay. Okay, so confirmed by the the both is the Formosa 3 data or itself compare. Okay, so you can see the cooling there exist. On the other hand, and I think most of the audience is well understand so-called the GPS one, and the GPS one actually with a 2 signal and with a time delay, you will be able to derive the total electron content quickly. And this is one example observed over Taiwan, and we have local time and UT time. There's 8 hours differences. So we shift over we plot on the local time coordinate. You can see the density actually is going very they reach very high altitude, very high value during the noon time and around the 4 p.m. This is Yang-Ming San. Okay, if you're familiar with that one, and that's Yang-Ming mountain is near the Taipei. It's very famous. And by the way, first of all, I'd like to mention all my data is the best part is we actually we would like to be able to let everybody can check it. So I'm using the data. Most of my data is public available. So if you don't feel comfortable or you don't like my data, go ahead and check it. Okay, the data is going to be, they'll let you check easily. So the other one, I use the data as 2 hours. Actually, the data is which is a 1 hour time resolution. 2 hours, that's because I'm going to use it, for the previous data to validate that one, see if they are whatever we see is agree with the previous or not. Okay, draw your attention over here. You can see that one, the top panel A, and the first 3 days is I marked that one with SIP period. That's because if you see the panel C, we have seen the positive, come up, on the August 1st and August 3rd. And the earthquake occur on the magnitude is over the August 5th. And you can see that one, the stone DST index, although the solar radiation maybe is higher somehow, but compared the stone one, that's still a little bit lower. And anyway, the stone is occur, let's focus on the 26 to 26, 27, and 28. And the other 3 earthquake occur on the 17, 19, and 20. And so on the, I was drawing attention over the, the panel B. You can see the, the August 1st. You can see that these are 2 spots. That's meaning EI crust. They go to very north, very polar. What that mean? That's meaning we have very intense electric field in eastward, and that's a result of this problem. Similarly, you look at the, on the 14th, and maybe some of the 15, and also 17, 18 August. All the the EI crust, they move very forward. Okay, and the other one is actually coming down here for the 26th. You can see that one is very, very huge, very intense, very dense over the TEC, and together the the crust expand very forward. And similarly on the 27, 28. So we coming down here, and you can see it's very amazing because we don't see any negative anomaly in the whole month. In fact, I told you the truth. In my case, I don't see that even. It should be go like 50-50, or like somehow they should be the same. Okay, but for this month is completely not that as we expected. But anyway, I'll draw your attention for the magnitude panel C, the magnitude 7, and for the 2 days before, 4 days before, you can see the positive anomaly. Similarly, there's a lot of the earthquake, and you can see the 2 days, 3 days, 4, 5 days for the first one. For the magnitude 6, you can see how that occurred, that related, and this is also denoted over the the previous table, table 1. The same thing for the same earthquake on the same days. And for the storm, during the storm, you can see very huge, intense, the electron density increase on the positive anomaly. And simultaneously, we use it, almost like a 320, the earthquake over the whole region. This actually is a fire ring, the Pacific Ocean, Pacific Ocean, and the West Pac. So West Pacific one, and then we use all the available data, magnitude 5.5 and greater, and to check whatever, as we know that if this is truth, this somehow this kind of so-called precursor or the pre-earthquake phenomena, they should be repeatedly appear. So since our GIM is available after 1999. And so when we use it, the data before, the earthquake, better not to use after, because that's going to, get the challenge. Say, hey, come on, you use the same. That certainly that will be the same. So okay, I usually collect the data, always use it before. And if we whatever we did it, we calculated exactly like what we did over here. I forgot. I'm sorry, I forgot to mention that one. For each time point, we look at the data, the previous 1 to 30 days. So we find out that at each time point, we found the 30 time points is a median value together with the upper quantile and lower quantile. And to enhance that one, we times, those so-called quartile range by 1.5. That's meaning like a sigma, you intense to become 1.5 sigma, something like that. And anything exceeded your upper bound, you say declare that one is a positive anomaly. So for example, this upper bound, you exceed that one, positive anomaly. exceed that one, the upper bound, then the positive number will plot over here. Similarly, anything exceed that one. So I don't say that's anomaly. It's just the data tell me this is a very strange compare previous 50 days, 15 days, 30 days. So we're doing the same thing over here, and we did the same thing, but not only for the the one. We checked 320, and exactly the 30 days before, 30 days after. So put together. So we calculated the proportion which is the previous the so-called 30 days before and 30 days after of the 320 earthquake, and superimpose that, and we calculate with the so-called one sample test, and so that will need to compare the background. That's meaning the almost 19 years overall the so-called positive anomalies occurrence rate. And I have we require, so whenever we say this anomaly exists, we need a so-called signal level should be exceed the so-called signal level 0.05. I think everybody know that that's a very stringent. So if I make mistake, that's only 5% and less. Okay, so I'm sorry. Then we found that this is an earthquake line. That's meaning from the 6 days and the 3 days during this period, the anomalies has been repeatedly appear over previous 320 5.5 earthquake. Okay, certainly you might complain a little bit and say, hey, this is very far from the earthquake. In fact, we also conducted over the region. Result is very similar, although it's not so beautiful of this, but I think they are compatible. So this is the whatever we extend, whatever we just observe. Actually, I really see that. Okay, so what I did actually, I used it, the data over the monitor this region. Whatever we just did, we monitored only that point, that area. So for those is a so-called time study for all the study here, and the other one we actually we monitored the data over this is a so-called slip, and so that will give us exactly on the panel B. Okay, so positive anomaly, and everybody almost know that one for the daily dynamo, and you're going to see the polar electric field, polar the crust. So that's actually up here. I already mentioned that one, so I can save my time. And so you can see I will say during the storm period, you will expect to see the positive electric field. If we can calculate this electric field for the properly over the storm, then we should be able to properly estimate SIP what's the electric field. And so we even will be able to see the storm electric field is caused by what. Okay, so if that's what I'm saying. We conduct space weather both from the top, also from the below. That's meaning lithosphere. So whatever we just observed for the globally 5183, and we calculated that this is 72 hours is the time period. That's meaning from 00 August 1st to the 24, the August 3rd. So 72 hours. And so we calculate each 5,000 all the letters, and we calculate and they say count is how many so-called positive anomaly occur. And this is the proportion, the anomaly percent, how many time point occur during that letters. And here is greater than 65 occur over here. Hey, globally you don't see anything, okay? And so I still don't give up. So, okay, how about before those 3 earthquake, those anomaly, let's put together. Okay, we got here. And then you might say, hey, we have there's 2-3 points over here. Yeah, you don't forget the one. This is around the so-called either the MEDE, so-called the meteoritic electron density enhancement. There's some other, the ionosphere phenomena. And for this one, that's so-called plasma pulse location. So this is for the together at the all together. So include the 7.0 and the other 3 magnitude 6 points the earthquake all together, and count the percentage. If anything exceed the top the percentage occur only these 2 points. So mostly, actually, most frequently, they occur over the the epicenter area. If we focus on the 7.0, they're over here. Similarly, we all know that the during storm period, ionosphere will disturb. If they come from the penetration electric field, they should be able result in or cause a lot of so-called positive anomaly. And you can see how many positive anomaly occur during those 3 days period. But I should also draw your attention, 75% all the time. Okay, and so anything greater than 70%, I just extract and highlight over here. So so whenever the storm, that's a global effect, you should have it everywhere. If you have an earthquake or some local event, I should be somewhere over the the specific region. So always a small area. And they say, hey, Tiger, this is very lucky, and this is a coincidence. Oh yeah, right. So if we measure that one, let's do it with this CSAT. How's that? Okay, a CSAT actually provide 4 different physical quantity or 4 different parameter. And I draw some line and how to, define how to define so-called anomaly. For the density, it should be greater than half. That's meaning it should be greater than their medium and or reference. So I choose it, with 50% and greater. Okay, sorry, this is not percentage. This is how many the density should how many should be exactly like the medium, should be greater than medium. Then I identify that's meaning if density increase for the both for the ion and the temperature. As we know that cooling, so we go more stringent one, which is below the first quarter. That means less than the 2.5. So we look at that one. This is the top panel. This is top 4 panels. This is A, B, E, F. Those is the daytime. So it's electron density, ion density, electron temperature, and temperature. So we put all together and choose most, the highest frequency during the those earthquakes period. Then here you can see this earthquake, the location, and this is the highest, the frequencies location. Similarly on this one, similarly over here, this all 4 on top of the this area, they have a coincidence. The parameter, they go all together and completely different physical parameter, and together with the earth, the TEC, they all go together. We are so interesting. So let's look at nighttime. That's mean the early post midnight, and only occur in the ion density. So if we put all together, this is for 7.0, and one of a figure, the overlap over there, and this is one of the 6, and pick up the most the highest, the anomaly altogether. For that we put the 7.50, 7.0, and the 6 plus, the S, the earthquakes all together, they over here. Okay, this is for during the, that's exactly I show over here. That meaning post noon, the electron density, ion density, electron temperature, and temperature, which is a post midnight is the ion, the density. The most funny places that stuck together. You see where's the most parameter they occur when crazy. We are so lucky again. Okay, so okay, we are lucky. Then how about the storm? You are so lucky. Then you can see that on top of this all the parameter we choose it whenever for the distribution of the 7 point the greater than the 25%, less than 75% for the electron and ion temperature. The same criteria whether we did it previously. Then you can see this is for this all together. Then we stacked, what those is when there's a highest consensus, they all come from here. Okay, so again, this all come from South Hemisphere, and similar to over, the one we observe for the TEC. So let's put all together. Left side, the SIP for all the earthquake together, and you can see over here. For the CSAT, specific over here. So, well, we are so lucky. There's this coincidence. Oh, yes. How about the stone? Same thing, okay? Right, just everything is, South Hemisphere. In fact, look, their pattern even very, very similar, okay? So something is out there, okay? Something has happened. For a stone, certainly we acceptable, widely accept. How about SIP? And I don't think we should have a double standard, right? Okay, so we looked at the stone, in fact, the LISA, 2020 and more, they also in 2021, they use the ON2 ratio, and you can see that the South Hemisphere, they are all well agreed, okay? So during the same stone. So that can explain a little bit about by using the ON2 ratio. Now, let's move on the most challenging one. Let's find out what caused the such kind of so-called anomalous signature, especially for those the electron density, ion density, ion temperature, and velocity. What I would like to begin with, this is actually kind of a new approach, because in previous, all the most of the scientists, they study earthquake precursor, they're using so-called scalar parameter, like electron, ion, temperature, and not very often been use it, so-called vector parameter. That's like the downward velocity, eastward velocity, northward meridional velocity. Okay, so the ion velocity. So this is a vector. The advantage of the vector parameter, I already showed you based on use it, dynamo process. We can all to know that if we know the velocity and we know the ambient, magnetic field, we can derive electric field. Okay, and we subtract, the so-called anomalous period, the electric field, and by the the reference field. Then we can estimate so the electric field for the seismoanalysis precursor. No, that's just that. Also, I can put the stone, anything, any period, we can do that. Okay, so the key is to use it, the ion velocity to to derive it. And don't tell me you're going to do electron velocity. That's impossible. Okay. So similarly, I kind of a curious person. So what I did actually, I using so-called box plot. And the only things I get a box plot because ionosphere data is under the so-called heavy tail. And I'm going to use it, the so-called, this is a non-Gaussian way to do that. Okay. And this is on the, the left panels, that's so-called PEIA, that's mean also SIP. Okay, seismoanalysis precursor, because some reviewer doesn't like SIP. So I said, okay, if you like that, pre-earthquake anomaly, that's the same thing. Okay, and the gray color stand for the reference. The reference, that's meaning I extract take those anomaly days out and construct the so-called the distribution. The upper bound, that's a so-called third quantile. This is the second Q2, that's the second quantile. This is a first quantile. And this median value, in short, this is upper 75%, lower 75%. And this is for the magnitude 7.0. So this is the data distribution. So whenever my upper bound doesn't overlap with this one, that's meaning they are statistically significant. Okay, this is a very coarse one. In fact, we check all the data by using so-called Manhattan U test. That's meaning very robust. The non-parametric. That's that's the other talks. Okay, so I'm not going to talk about that. And this showed that during during SIP period, the downward velocity actually this become very upward. So that's completely going up very high. And this is a result from what? So we can take this this mean difference, medium difference, then derive the the electric field. The electric field become 2.21 eastward. And so we did the same thing for the other. We didn't calculate that one because this is not exceeded the upper bound, but we somehow notice that it's mainly due to the 7.0. So we calculated the ones, by the way, we checked this one. This is also okay. The not too bad because we calculated with Manhattan, U-test. We checked that this is significant. So we compute, the result. For this one, the shape of these boxes are very different. Again, we checked that one. The Manhattan is okay. Okay. So it's similarly, box price is only a very coarse one, but real one should go to the Manhattan. So whenever they are significant, we calculate the value. So in short, for the earthquake, SIP period or the PEIA period, perturbed electric field is going to the eastward, and for the eastward velocity, this is like a downward. Okay, so the downward eastward, that's for the SIP. Let's look at the stone. This is stone. And again, you can see that the box is completely different now. Surely this is, we can calculate it with mid, signal level. That means they are very different. So again, this is a westward. Oh, they are different. Okay. And for the daytime, eastward. Okay. And this is downward. This is upward. Remember, this is a feature. This is very, very important because this is going to tell us not only the magnitude. We always see what's the cause of the storm. Everybody, if you're interested, look at the catalyst. This figure. This is a talk about the region 1 current due to the the solar wind, and this is due to the again solar wind, the region 2 current from the west side and going down, and this is from east side going up. But for region 1 from the east side, from downward and going up. And so here, if the region 1 is stronger, that means electric field going this way. Okay, and so region 1 greater than region 2, eastward, the current eastward. In the ionosphere, they are motor. Okay, that means electric field going stronger over here. Day side, solar is on this side. Day side eastward, night side, westward. Okay, so this is meaning the the eastward in day side, westward in night side. That's the region 1 greater than region 2. That's our so-called prompt penetration electric field. Okay, that's a stone. So if you're working on stone, that that's the baby. Okay, so the CSET plasma quantity can be used to prompt ionosphere space weather and the plasma depletion, the non-migraine type, mid-latitude trough, and the magnetic stone, seismic precursor. Okay, I did not show you the middle latitude, but in fact they can do that. Okay, trust me, I already demonstrated whatever the all possibility, and in fact we would like to calculate the electric field for those PDP and the WM4 in the future. Spatial analysis showed that the significant increases anomaly of the CSET electron density. And altogether with the the GIMT frequently appear specifically over the epicenter 2 to 4 days or 1 to 5 days before the August 5th, the Lomo earthquake, together with M6. This indicates that meaning SIP has been observed. Okay, because I did not show you how many letters versus 5183. If you don't believe that, cover your eye and turn around and make some circle and shoot with a dartboard. See if you can shoot that one exactly on the, actually you can hang on the wall and shoot at your dartboard. You can hit it. I would say you're amazing, okay? And you hit all the time, and with different kind of error, then that's you're super. But I told you that the chances of this is not related to the earthquake, it is very, very small. Poleward motion of EIA for the EIA crust indicate that the electric field enhanced during SIP period and the storm period. In fact, we recently wrote a paper, developed paper, submit to the Space Weather. We're using the EIA, crust motion to estimate electric field. So in the future, we can derive the electric field not only by the satellite, the in-situ measurement, but also we can do that by using, the EIA crust. So for the CZ ion velocity, we found the SIP-related electric field over the epicenter. It's about 0.21 and 0.02 millivolt eastward, okay, and 0.04 and 0.13 millivolt downward in the at the I'm saying at the 2 a.m. and 2 p.m. 2 to 4 days before the M7.3 earthquake. The one thing I just draw your attention, I have a little bit skeptical about 0.14 and 0.13 downward electric field because I am a little bit skeptical field line, the electric field to be computed. Prompt penetration electric field, okay, caused by the significantly costly increase of electron density ion density during the intense DST storm. So know that we already know that the electric field is fully, caused by the region 1, region 2. Primary electric field is 0.17, 0.06, downward, and for those, the day side, night side, they are different. Okay, so what I would suggest that go ahead and check, that those is electric field in eastward, westward, and in all the existing publication, there are many. Okay, you will see the value is very reasonable. The best part actually, I already mentioned that one for the storm. You have increased. We are increasing the activity current region 1 greater than region 2. So based on our result, even the not only the eastward, westward during the storm, but also downward, upward. And you look at the downside and dusk side, electric current exactly meet all the the estimation. Thank you for your attention. This concludes my talk.
Yeah, thank you so much, Tiger. And any questions? Please raise your hand or write it on the chat box. It says that how about EQ that occur at higher latitude, bigger than 30 degrees north-south, outside the tropical region, such as at the magnitude 7.8 earthquake at Turkey, Syria, on the February 6, 2023.
Oh, I'm not going to tell you that.
Numbers. Yeah.
That's my ongoing study. The answer is yes. We already see a very interesting phenomena. We already found the anomaly. That's a positive one, but we haven't yet calculate the electric field. And in new the new data sets, we actually have an even more powerful way to identify the earthquake, the anomaly by using a GMTEC. For the latitude greater than the 25 or even greater, we suggested to use it either CSAT or use this Formosa 5 AIP to calculate electric field and ion plasma quantity. For the earthquake below the 24 latitude, both north and south, please you can use it. The Formosa 7 IVM. I noticed that ICON might have some data delay, so I don't know exactly what happened. And the other one for the high latitude still can use it swarm or other the satellite. I hope swarm still alive. Yeah.
So does that answer your question? Any other questions? I mean that you have mentioned this from the TEC. How about in situ measurement using maybe, let's say, the ionospheric plasma density, temperature? Would that also tell you, give you some information?
Well, what I just mentioned, that's a use based on the in situ measurement. If for the GIM-TEC, you can use everywhere, from North Pole to South Pole, almost.
But now that we have thousands of this kind of small satellite, low latitude satellite, would that be nice to have ionospheric probe on each of them?
Yes.
So the other question is Alex, do you expect the difference in the positive negative TEC for the tropic and middle latitudes?
Yes. In fact, it's not because of latitude. Originally I thought that's come from different, the latitude. The latest study shows it, it is actually the not only these are decided by both the underground structure. For example, in China, there's usually you will see the negative anomaly, or say the decreased anomaly. For in Japan, same latitude, you will see you frequently see the positive anomaly. And the other things is actually the same location. You will be able to see like Taiwan, you may see the negative anomaly maybe 1 to 5 days before. But if you look at the 20 days before, that's you come up with the positive anomaly. So the anomaly of the so-called polarity, in my opinion, depends on various things. One is certainly will be the underground, the conductivity, so-called the electromagnetic property, and also the process of the so-called earthquake, the generation.
Thank you very much.
Okay, there's one from Noru Chokuma, and he asked that what could be the phenomenon that occurs between EIA and electric field enhancement?
Oh, for example, for these cases, in Indonesia, if an earthquake, somehow, if the atmosphere was somehow, electric field was superimposed with a daily dynamo, because every day around 8 o'clock, 6 o'clock a.m., due to the solar radiation, we start to have so-called dynamo electric field. And the dynamo electric field could reach the highest value around 10 a.m. and ended by the maybe around the 5 p.m., 6 p.m. or 8 p.m. So every day you will see the positive, eastward electric field, very, in the local time. That's in especially over the equatorial, the ionosphere. And if during the storm, penetration electric field generated from the high latitude, they superimpose that one, then two electric field add together, you have a much stronger electric field. Or like earthquake, underground, process for some reason, they, generate electric field. They superimpose with, the so-called ambient dynamo electric field. So that will certainly uplift your plasma to a higher, even higher altitude, then subside down to the further distance toward poleward. So many things can affect the daily dynamo.
Okay, very good. Any other questions to Tiger? or you have questions to the audience instead?
Well, I'm good. You know, I'm just very thanks and very grateful you invite me to give such a challenge talk. You know, because for our honors scientists or space scientists, we many interested in so-called physical mechanism. If we see the statistic, but without any information, any knowing about the causal of the SIP or the PEIA, that's still have a little bit sad to you know, did not know that. I would like to mention this is actually open a new you know, it's a chapter because we now using the ion velocity. So and we can use ion density to cross-check the TEC. We can use electron density to cross-check the, you know, the TEC. So the, you know, the based on quasi-neutrality, all the, you know, information, all the result, they should be consistent. That's the physics. And if we know the physics, so we are getting one more step toward uncover the secret of the earthquake precursor. Then that also have some so-called quantum breakthrough toward the earthquake forecast or earthquake prediction, because this is physics. This is not just by chance.
Yes,
that's all I would like to mention.
There's a after your answer, there's a comment from Anuru Chukuma, I think. That he said that most of times there is a negative TEC during the eastward electric field, which could make it very complex.
I'm not yet to study all the detail. Actually, the eastward electric field in the low latitude should most likely cause the positive anomaly. Certainly, if you compare background, original place that will look like negative. So actually, that's the reason why, you know, that the true reason is just because your EIA crust move even forward. So if we subtract the TEC by the reference, then the original place is going to be negative. So that's if you base on the EIA crust, that could happen if the location is look like that. But we mentioned over here, I would like to mention over here, because your density over the right above the, your EIA, earthquake, then that's going to be difficult. But I would like to also offer you one more, the latest development. In fact, Formosa 3, Formosa 7, they allow us to construct a 3-dimension. So some lower part could be, your plasma or electron density uplift to higher altitude. The original place comparing with your reference state could be negative, but the above is going to be positive. So this is a kind of a complex question, kind of complex, so in the future, actually, we are ready to do that. We're using a 3-dimension, not the, only 2-dimension.
Okay, we look forward to, to your new results. Any other questions?
The final,
yeah, go ahead.
Always, the final question always, it is a precursor or a trigger. That is the point.
One more time.
It is what you observe, it is precursor or a trigger?
I will say, the ion density, whatever, they actually is, I would say the response. This is the signature from the lithosphere. So I would say this is a pre-earthquake signature. This is the response. It's not the causal, not the trigger.
Yes, yes, I agree. That is an indicator or a manifestation of something. Yeah, and
Yes.
this manifestation is this manifestation of the preparation or a manifestation of some kind of trigger.
I would like to say this is not trigger because I think the plasma just obeyed whatever the outside. So I don't think it's a trigger. It's just the communication or the response.
All right, good. Thank you so much. I think that we have 5 o'clock exactly, and thank you very much for coming to the seminar. I think that we are looking forward to some other new results, even actually about this the big earthquake just mentioned. I think that the Professor Liu is working on it, so we will finish this session today right now, and thank you again. Thanks again, Tiger.
Okay, you're welcome. Yeah,
Yeah,
bye.
bye.
Everybody.
Bye.
Bye. Bye. Bye.